Vivek, would you hit the button? Okay, welcome everyone to our weekly IQS seminar. We're happy to have our own Mordecai Waegell give our seminar today, who needs no introduction, but nevertheless, I'll give one anyway. Mordecai did his studies at Worcester, Massachusetts, and then came here to Chapman as a postdoc and has been here ever since. His interests are in the foundations of quantum mechanics, and today he'll be telling us about local quantum fluid mechanics. Mordecai, we're happy to have you here with us.
Thanks, Andrew. All right, so this is going to be a little bit of a detour from my usual talks about Bell's theorem and philosophy of physics. This one is much more technical and really just about interpreting the Schrodinger equation. Some of you have heard my talks about many worlds, and this has a little bit of a connection to that, but really that's not the point of this talk. I'm going to kind of try to pass over that quickly and get into fluid mechanics using the single particle Schrodinger equation. So the basic premise of all of this is that we can interpret the Schrodinger equation as describing a conserved flow of a fluid that moves in space-time. There's a local many worlds interpretation, which I'm not going to spend any real time on today, where you can take any entangled quantum state and break it down into an ensemble of these fluids in space-time, not in configuration space. So you can put all of the physics back into space-time. Once you have that picture, the dynamics of that fluid in spacetime are classical, except that there's a new type of energy that you have to ascribe to the particles. You can think of that as sort of an internal energy. And once you have added that energy into the dynamics of the particles, the equations of motion are all classical. But that new quantum potential energy explains a lot of the weird quantum phenomena that we see. So it explains tunneling, interference, penetration into barriers, that kind of thing. So very soon after Schrodinger published his famous equation, I think it was just a year later, Madelung recognized that you could interpret it as an equation of fluid dynamics, where the mod square amplitude associated to the Bohm rule probability is interpreted as a fluid density. So we're going to see these three symbols appearing throughout: rho, r squared, and the mod psi squared. Those all describe the density of a fluid, which would have been the probability density in standard quantum mechanics. But that's the underlying point of the interpretation. So we're going to take probability and interpret it as density of fluid.
Although Mordecai, presumably this is before Bohm came along and made his contributions to the field.
That is true, yeah. So this is sort of a retrospective picture of how this all fits together. So the main thing to understand is that we're going to take a single quantum particle like an electron, which is described by a Schrodinger wave, and we're going to interpret that wave as really characterizing a fluid. So one electron will be comprised of a huge number of fluid particles, really an infinite number, because we're talking about the continuum limit of the fluid. So we're going to treat the fluid as a continuum. But the idea is that there are some particles underlying that. So one electron, an entire fluid of classical particles. Two electrons, more fluids of classical particles. So the original Madelung-Bohm equations, Bohm basically took the same equations in the 50s to develop this interpretation. It wasn't really a fluid picture anymore at that point. But that all happens in 3n dimensional configuration space. And the local many worlds interpretation allows us to replace that with a bunch of different non-interacting fluids that are all in space-time. So back in 3 space dimensions and 1 time dimension of special relativity. And again, I'm not going to spend any time really about how that works, but if anyone's curious, I'm happy to explain it later. So we're going to start with the non-relativistic single particle Madelung-Bohm equation. Once everything's back in space-time, that's all we need. We don't have to deal with the 2-particle or 3-particle equation. It's just many copies of the single particle equation. This is the non-relativistic case. Back.
All right, Sarah, we're gonna rely on your editing skills.
I don't know about that one. Our audio completely shut off.
I can do that on YouTube.
All right, continue.
All right, so where was I? All right, so in the local many worlds interpretation that I'm not going to spend a lot of time talking about after these first few slides, the elemental fluid particles follow world lines through spacetime. Each of those is associated to an elemental world for that system, and the density of the worlds matches the Born rule probability to find each outcome state for a measurement. So we get the Born rule probability out from a frequentist experience of the Born rule probability, just because your experience will be tied to one of these fluid elements on a given trial of an experiment, and the density of the fluid elements literally matches what the Born rule probabilities say they are. All right, so I think that's mostly all I have to say about local many worlds. So now we're really going to focus in on space-time, single particle Schrodinger equation. So we have a bunch of different fluids. I'm really just going to talk about how one of them evolves at a time. That's going to be the rest of this talk. So we're not going to really worry about the fact that there are many fluids anymore. Each one of them evolves according to the single particle Schrodinger equation, and the fluid comprises classical particles. They have standard momenta, they have standard kinetic energy, external potential. I'm calling those subscript A for average, and I'll explain why those are called averages later. But those are essentially just a classical momentum and a classical kinetic energy. But we have to add this new quantum potential energy term in order to get the right classical equations of motion to describe our fluid and be consistent with the Schrodinger equation. So we're going to interpret that new thing, the quantum potential, as a kind of internal energy. It can become negative, so it can become negative and provide back some kinetic energy to the particles, and we'll see that's where a lot of the interesting sort of non-classical phenomena come from. So,
Question about point one. Are there an infinite number of particles in the fluid or a finite number of particles in the fluid?
it's probably an infinite number. Again, we're talking about the continuum limit of the fluid when we use the Schrodinger equation anyway. So if there is a finite number, we of course grained over them to get a continuum. So there has to be some scale at which we're doing that, but I'm not really going to worry about that detail very much in this talk. So the end result is that the total energy of a single classical fluid particle is the kinetic energy plus the external potential U plus now this quantum potential Q. So that's our total energy for these particles. And I'm going to show later on in this talk that in order for the fluid to locally conserve energy, it actually has to be possible for the energy in Q, that internal energy in the fluid particles, to spread between fluid particles rather than just being carried along as they move. So there's going to be a kind of diffusion of that energy. And that's something we need in order to get the picture to really come out local, which is kind of the underlying goal of this, is to have a local fluid mechanics picture.
And so that would imply interactions in worlds in point one.
Yeah, I mean, the interactions between the different fluid particles are effectively interactions between worlds, but it's sort of before they really branched into what we would normally consider to be worlds. They're not worlds in the macroscopic sense. All right, so we're gonna treat the total potential energy of a particle now as the sum of these two energies, the external potential U and the new quantum potential. And then the kinetic energy will be relative to those. So that the force on the particle will be the gradient of that total potential energy, the negative gradient. And that's going to give us our equations of motion. Some of this is a little bit repetitive. So non-classical behaviors like tunneling and interference, they're given a classical explanation by Q. So once we think of Q as just a classical type of energy, it's going to explain a lot of these unusual phenomena that we see. So something very general we can say about what the quantum potential does is that it takes the shape of the external potential U and it more or less cancels it out. If you have some unusual shape for a binding potential, except where the potential would go to infinity, the quantum potential has the shape of nullifying the contours of that potential. And I'll show some examples of that you can see kind of how it works, but it's really easy to see it for an energy eigenstate. Because for an energy eigenstate, I've got no kinetic energy. The fluid is at rest in those cases. And so the total energy is just Q plus U. Each of these is a function of position, because we're talking about different locations in the fluid where the particle would have a given amount of quantum potential energy and a given amount of external potential energy. And those always add up to the total energy eigenvalue, so it's a constant. So the surface Q plus U is a flat surface for an energy eigenstate. And you can think of that as explaining why it's an eigenstate. There's no force because it's flat. The gradient is zero. So the fluid that's there with no kinetic energy just stays in equilibrium. it doesn't move at all. And you can actually, from this condition right here, that for an energy eigenstate, the potential has to be flat, you can rederive the time-independent Schrodinger equation. Just falls right out of this expression right here. So you can get sort of an argument in reverse that the reason we have energy eigenstates is that those are the particular configurations where the quantum potential and the external potential add up to a flat value so that nothing makes the fluid accelerate. So it's an equilibrium condition for the fluid. That's what gives you the quantization condition in the Schrodinger equation. Okay, so the main way to understand what's going on here is that we have this new quantum potential. It has some contoured surface like the external potential. It tends to cancel out the external potential. We'll see in dynamic situations it doesn't cancel it exactly. But it's a function of the density of the fluid. If you know the density of the fluid, you know the quantum potential. They're not independent things. And then once you know the quantum potential, it exerts a force on the fluid, which reshapes the fluid. So we have a kind of feedback going on. We have the fluid moving, and as it moves, it changes the quantum potential, and then that changes how the fluid gets moved. So I'm going to really try to get that point across in an example here. So we've got an example of tunneling and a superposition of the ground state and the first excited state of a quartic double well potential. And so what you'll see here is that Q pretty much cancels out the shape of the potential. You won't really see the shape of the quartic potential at all anymore. And then we're going to get an extra dip in Q, which actually drives all the motion of the fluid. So this is a little movie of that. So the gray line here is the external quartic double well potential. You see, we've got down here, if you look, we have the density of the fluid, which you can see just by the density of these dots. These are going to be tracking streamlines in the fluid. This is really a one-dimensional fluid, but I've shown the dots up here too, so you can see what energy level they're at. But really, this is all the motion is actually down here. So I have curves for the external potential. This blue curve is the total potential, the sum of the external potential and the quantum potential. And then this is a superposition of these two energy eigenstates. So the lowest one is this light blue line, that's the ground state. The top one is the first excited state. And then the expectation value is that line right in the middle. It's an equal superposition of those two. And so at this moment, time zero is actually a singularity in the quantum potential. So this goes all the way off to negative infinity. But as you'll see, that singularity disappears as soon as I let this start to time evolve. So the point is that as the fluid moves, it's going to change the shape of this blue curve, because the shape of the blue curve depends on where the fluid is, depends on the density of the fluid. And so as the fluid's going to move in this potential, and then it's going to change the potential dynamically as it moves. So we have this continuous feedback between the two. So what you're going to see first is that these start to fall into a well, and then they come out and end up actually higher on the other side, which looks counterintuitive. Classically, if I just had a static well, that wouldn't happen with energy conservation. But what's happening is the well is moving. So as the particles are falling through, the well is actually pushing them up and giving them some extra energy. That explains how they can get to the other side. All right, so let's watch this evolve. And in case I didn't emphasize it, what we're looking at here is tunneling, because classically nothing would be able to get past this barrier in the middle here. So this is just time evolution of the Schrodinger equation, but evaluated with these particular quantities in mind. So you see that the total potential energy is this blue line. So the quartic potential is just gone. Basically, we've gotten something flat, and all of the motion is being driven by this dip, which moves along, kind of pulling the particles across as it goes. And it's a little bit more complicated than that, because it's not just that these particles are falling through some static potential well. The well is moving as they go and interacting with them and exchanging energy with them. Anybody have any questions about what happened in this movie? Yeah.
Seems to me like you can answer a question about how long they take to tunnel pretty.
Oh yeah, directly. Yeah.
Sort of the speed.
Yep.
So have you compared that with various literature controversy about tunneling?
I haven't dug into it too much. I know there's a bunch of people who say that tunneling happens instantaneously, so they must mean something different than what's happening here. But yeah, certainly if you track the particles in this fluid, you can see that there's a finite passage time across the barrier.
By the way, in particular, there's an ongoing recent controversy in the Bohmian mechanics literature about precisely whether this tunneling time here is the tunneling time that would be measured in an experiment. So this is ongoing.
That's why I was asking.
But I mean, one thing to say about this is that it gives you a really, really simple, essentially classical explanation of tunneling. The reason that the particles tunnel through is that the total potential energy they see doesn't have a barrier at all. It's flattened out, and there's this additional dip that's driving the motion across. So by adding the quantum potential as a new kind of energy, instead of this particle potential, we're seeing this blue line as a total potential. So the dynamics is totally different, but classical given that energy surface.
Related question, suggestions. So there is this effect called the Hartmann effect, where you make the barrier longer and longer, the tunneling time, effectively the velocity exceeds the speed of light. Have you calculated the velocity of
I haven't, well, this is all non-relativistic. So the velocity at that singularity you see at the beginning actually goes towards infinity. So that's something that I think the relativistic case will fix. But in this picture, we get infinite velocities. So we're not ready to really say we have full locality yet. As I said, a lot of the lessons that we're going to get here, I think, carry over into the relativistic case, but there are some details that have to be treated really carefully.
So imagine if you let this movie play continuously, would just go back and forth.
Yeah, it only does 1/2 of the period. It would just it just cycles back and forth symmetrically. Yeah. Okay, now if you stop at a quarter of the period through here, when this dip is right in the middle, I'm going to show you kind of how the analog of this looks for a couple of other different potentials. That's the next slide. So here we are right in the middle. Okay, so over here is the quartic double ball potential again, and this is at t/4, so a quarter period, so it's halfway through that tunneling process. If you look at halfway through the tunneling process for a finite rectangular barrier, we see pretty much the same thing. We have the shape of the external potential has been canceled out, replaced by this thing with a dip in the middle, with a corresponding spike in the local kinetic energy density. And if we look at the infinite square well, we get pretty much the same thing. So these are all superpositions of the first excited state and the ground state. They're all oscillating back and forth in pretty much the same way. And the point of showing this is that for all these different external potentials, different ways of getting the ground state and first excited state, the shape of the external potential plus the quantum potential looks pretty much the same. And the motion is being driven by this dip. If I made movies of all of these, it would look almost the same as the movie you saw for the tunneling case. Somebody have a question?
Yes, what does the dip depend on?
Well, again, it's just a function of the fluid density. So remember that the blue line is the sum of the external potential and the quantum potential. So the quantum potential is not only canceling out the harmonic oscillator potential here, it's also creating this extra dip in the middle here. Though you can say in some sense, maybe it's just leaving part of the dip, though it does go negative. It goes below where the harmonic oscillator would have been 0. I should be careful here because the units are different. The external potentials are shown kind of without units on here. And the units are showing you the energy densities, the energies for these curves, the corresponding energies for the fluid particle. Any other questions?
There, most like this. Looking at the movie on the previous slide, there's some sort of like osmotic interpretation of what's going on, potentially.
I'm not sure what you mean. There's something that people call the osmotic velocity. I'm going to give it a different name, but
just like osmosis influence in terms of like density, like differences.
I mean, in the sense that that's following essentially classical equations of motion.
Yeah,
yes. Sure. So yeah, there's certainly an analog. Okay, so now I'm going to talk about this thing. I call it the symmetric velocity. It's been called the osmotic velocity in some places in the literature, but I haven't this name symmetric for it for reasons which I think will become clear in a second. So this is going to come from an imaginary term that appears in the quantum momentum density. And the reason that we're not just neglecting it is that when you take when you apply the momentum operator a second time to get to the kinetic energy operator, it's that term that becomes the quantum potential. So it seems to be deeply connected to what's going on with the quantum potential energy. When we get to the kinetic energy density, there's an imaginary part there that we'll actually ignore it there for a reason that I'll explain. I might actually go back and look at it more, but it's not going to stop us from making progress along the route that I want to take in this talk. So we're going to define the symmetric velocity to be the imaginary part of the quantum velocity that comes from the quantum energy density. And I'm going to define all of these things more formally later on in the talk. I'm just trying to give the big picture right now. And what we're going to say is that the total velocity of a fluid particle is actually the real part of the quantum momentum, or the part that comes from the real part of the quantum momentum density. That's what we call the average velocity. That corresponds to the average momentum that I was talking about earlier.
Bohmian momentum.
Yeah. same thing. And then I'm also going to have the magnitude of this imaginary part, which I'm calling the symmetric velocity. And then that contribution is pointed in some arbitrary direction. And I'm going to have at each point in space-time, I'll have an ensemble of particles. So I don't really have something like classical fluid where I have to have one particular streamline velocity at a point. What I'm going to say now is that at a given point, I've got particles that are going in a bunch of different directions. They have different velocities. And the velocities of the RI, the symmetric components of those all add up to 0. So they don't contribute anything to the net flow of the fluid. So I have this average part, that's the one that's going to be associated with the fluid, the flow of the fluid. And then this extra symmetric part, which because these directions all sum to 0, doesn't contribute anything to the flow. That's why I call this symmetric, because it always has, the directions always summing to 0. And if we average over I, that's where I is the ensemble of different elements that are at a given location, then we're going to get back just the standard average velocity. So all of these terms sum to 0 in the average. And that's going to give us the average flow velocity, which relates to the average kinetic energy. And those come out from the real part of this quantum momentum density. So I'll explain all of that in more detail later on.
So symmetric velocity is equivalent to the osmotic velocity.
Mathematically, they're the same object, but the way that I'm interpreting them is different because the osmotic velocity has a direction, and I've basically just taken the direction and killed it. I've said absolute value, and then we're going to add on these arbitrary directions that go in a symmetric orientation, but I'll justify that more as I go along. Okay, so if we assume that there's this Vs, there would be an associated kinetic energy. But if I'm saying this is the energy of a particle, and I take V squared to get a kinetic energy, I'm also going to have cross terms VA and Vs. And so I can't really have two separate kinetic energies for one particle. It only has one velocity, it has one kinetic energy. But what we're going to show is that when we write down the quantum potential, there's a really natural way to separate it out into a reduced quantum potential and this term that looks like the kinetic energy for the symmetric velocity. And the fact that we have those cross terms isn't actually going to be a problem because the average classical kinetic energy of a particle averaged over I, so at a given location averaged over all the different directions the particles might be moving. When I take this average, all of the cross terms between the different VIs all cancel out. And so the total classical kinetic energy on average breaks down to just a sum that looks like these two separate kinetic energy terms. That's because all the cross terms cancel. So even though it seems odd to have a sum of two different kinetic energy terms, that's actually what happens. That's what comes from the single classical kinetic energy term corresponding to this velocity distribution. Okay, so then we'll get a classical kinetic energy density in the fluid that's just R squared. Again, that's just the density of the fluid times whatever the corresponding kinetic energy at a given location would be. Okay, so I'm gonna skip ahead and talk a little bit about the properties of these things. So this is the form of the reduced quantum potential energy density. I'll derive this in a little while so you can see how it comes about. But you see it's just the Laplacian of the density times a constant. Because it has that form, it has this property. If I have a normalized function, R squared, normalized pulse, then we can say that at plus and minus infinity in one dimension, it's 0. And from that, it follows that if I integrate the reduced quantum potential energy over the entire system, that comes out to be 0. And that's this proof shows how it works in one dimension, but it actually generalizes to 3D pretty trivially. So whenever we have this kind of density defined as the Laplacian of a normalizable density, the integral over this function is always going to be 0. And so in some sense, the quantum potential, the reduced quantum potential energy, once we separate out the symmetric kinetic energy from it, it holds no net energy. It kind of takes some energy from one part of the system and puts it somewhere else, but the integral over it is 0. So it's not that the whole function is 0, just that it integrates to 0. So it redistributes the energy in some ways, takes some away, provides some negative energy in some places, which allows some extra kinetic energy to appear in those places.
Yes.
Okay,
Is it the same as saying I create a virtual state and I go back to some other state with conserving the inertia?
I'm sorry, can you say that again?
When you are tunneling through quantum process, you can think of creating a virtual state and going back to the other state, but at the end you conserve inertia. So
I don't know. I mean, that's an interesting question. I don't know if it has a good analogy to, to the creation of virtual particles or something like that. I mean, this is a statement that's true at all times. As the dynamics of the system evolves, energy, might get more negative energy over here, and that will mean that some positive energy appears somewhere else. And so there's sort of a flow of this kind of reduced quantum potential energy. It leaves one place and goes somewhere else, but the amount of that is always conserved as well. It always sums up to zero. Yes.
So you previously showed that for a harmonic potential, the the U plus Q term is saturates. But here you said that the reduced potential averages to zero.
Yeah, so the reduced potential is not the same as the standard quantum potential. So this is the definition. The reduced one is I take the Q that we were talking about up until now, and I remove out this symmetric kinetic energy.
So what I mean to ask is that kinetic energy will be infinite for like large distance values.
For large distance values. I don't understand what you mean, actually.
So Q plus B should be constant.
Yeah, it should be relatively flat. Yeah.
So that means K should be infinite. Because B is a harmonic potential that goes to infinity.
Oh, yeah. So yeah, you're right. The kinetic energy of a particle, as we went further and further away, it does get larger and larger. However, the density goes down towards zero. So the number of particles we find there vanishes.
I see.
That's what I was not understanding the question. But yeah, technically speaking, whatever tiny number of particles you have, far away, because in a harmonic oscillator, they extend infinitely far. The tails go off to infinity. So yeah, at the very far end, you have essentially infinite kinetic energy. Okay, so for energy eigenstates, we have everything stationary. So the average kinetic energy is zero. That's the one that corresponds to the actual flow of the fluid. So if the fluid stays stationary, usually kinetic energy is zero. We'll see a case where that's not true, actually. But for energy eigenstates, it certainly is true. And so the total energy of a particle in the fluid, sorry, this is no longer a single particle. This is just the expectation value for the whole fluid. So integrating over everything would be the sum of the kinetic expectation plus the potential expectation. These break down into the sum of these four terms. So this is the classical kinetic energy. Remember, before we had K plus Q plus U, these two terms together are Q. I've broken it apart into a kinetic energy term that's always positive, and this reduced quantum potential, which always integrates to zero. So Ka is zero in this case. I just showed that the average over the reduced quantum potential is zero. So this simplifies down to this form. And what that shows us is that all of the kinetic energy, the entire kinetic energy expectation value in an eigenstate is coming from the symmetric energy. That's where the kinetic energy is. And so it really does make sense to think of that as kinetic energy rather than trying to imagine it as potential energy. If I work in the sort of standard picture with just the standard quantum potential, all of the energy in an eigenstate is in the quantum potential energy. And that seems kind of odd because normally we would think of these constates as having kinetic motion. And that's the next thing I'm going to say here. So there have been these time dilation experiments with muons, where you strip an electron off of an atom, put a muon into an electron orbit. And what you find is that if the classical orbital velocity of the muon would be relativistic, and you would get some time dilation in the half-life of the muon, that's what you see in the lab. So if you take the sort of standard picture for the stationary state where the fluid is completely at rest, you would not expect to get any time dilation. But if you now imagine that there is actually motion there, and the motion is, again, not changing the fluid density, but there's this symmetric motion. So the things are always moving with some extra velocity vs, that is consistent with the time dilation that we see in these experiments. So it's, thinking of the symmetric kinetic energy as a kind of motion which always cancels out so that the bulk fluid does not appear to move, explains what's going on there. And certainly if we talked about the corresponding classical system, like a particle found in a harmonic oscillator, it would be moving back and forth in time. So there are good reasons to think that there should be motion in these states. And so it was a little bit odd that the standard Bohmian Madelung formalism said that eigenstates would be completely at rest. If we pull out this kinetic or the symmetric kinetic energy from the quantum potential, now we get something that really seems to make sense. And again, that's the thing that corresponds to the expectation value of the kinetic energy anyway. Okay, so this gives us two different pictures that we can work in. This is the standard picture, the one we kind of started with, and I showed the figure in the animation for this picture, where we have a quantum potential and an average kinetic energy. So we treat the total Q as an internal potential energy. We treat Ka as total classical kinetic energy. That's really intuitive for understanding the bulk flow of the fluid, as in the animation we saw. But it seems to be slightly less physical because in eigenstates in this picture, Ka is 0. So we have a new picture where we treat the pair as actually being the reduced quantum potential and the total classical kinetic energy, the one that I got before, where I sum the average and the symmetric kinetic energies together into one term. So in this picture, the QR, only the reduced part that we know sums to 0 across the entire fluid, that's treated as an internal energy. And then it's the Kc, the sum of the kinetic average and symmetric part that give us the classical kinetic energy. Yes?
Yeah, I want to understand a bit more what's going on at the level of the particles in this fluid.
Mhm.
So at every point you have these two velocities. So
Or really, maybe more than 2. Yeah.
Yeah, but that's in one dimension. It would be 2.
Yeah, you're right. Yes.
So you have these two so are particles sort of still deterministic, continuous? So you have two particles passing each other like this, or is there some sort of stochasticity? A particle is choosing whether to go.
So I think it's not uniquely determined, the answer. There's different ways you can try to answer it. I'll give one suggestion for a way that it could work in another
So
slide
we
or
don't
two.
have the underlying dynamics of that.
No, I don't. Yeah. I just know that whatever it is, the velocities at any given point have to sum to 0 for the symmetric part. The average part won't sum to 0, it'll flow. But
This is why you made it symmetric. It's sort of taking an average quantity and then partitioning it into something symmetric on
Yeah, but the
average.
question is what you're actually taking the average of.
Yeah, exactly. So that's not specified here, I guess.
yeah. So basically that, to follow the idea that this term should be something, but I know it doesn't correspond to any kind of flow in the fluid, I needed to come up with some velocity distribution that would not create a flow in the fluid. And so they have to somehow cancel out if there's actually motion.
On average, it has to have this kind of symmetric.
Yeah, but that leaves a lot of possibilities for how that could happen. Yeah.
Oh, just to reiterate, this Ka, that's the Bohmian kinetic
Yeah,
energy, right?
and this Kc is what happens if you take that and add to it the symmetric kinetic energy term, which comes from the osmotic velocity. And again, that just falls right out of the quantum potential, which I'll show in just a few slides.
And what do you call that, classical?
Well, it's classical because the equations of motion are classical once you add this energy in. So you get a standard Hamilton-Jacobi equation with a Hamiltonian with that energy that I just wrote down, which add Q in there. And everything comes out from classical equations of motion. So it is quantum because I have this new quantum potential, but that's the only sense in which it's quantum. Yeah. So again, this is probably the more physical picture because we're including the symmetric kinetic energy that's apparently there in eigenstates, but the kinetic energy doesn't contribute anything to the flow, and so this symmetric one doesn't, and so it really does act more like a potential energy. So if you want to get an intuition for how the fluid flows, it's easier to work in this picture, which is why I started with this picture. But if you want kind of a more physical story for where the energy actually is, this picture seems like it makes a little bit more physical sense. Okay, so now we're actually going to get into the technical details a little bit. I've avoided this so far. So we're going to start with the Schrodinger equation. We're going to write the wave function in iconal form, sometimes called polar form. So we've got a positive real function r, whose square is the density. And then, oh, this is a mistake. There shouldn't be a negative sign there. This is always positive. I apologize about that. But yeah, and then we have the exponential of another real function here, s. That one can be positive or negative in general, and there should not be a negative sign there. So again, the r relates to the fluid density like this, the way that I showed earlier. And then this s is essentially Hamilton's principal function for this Hamilton-Jacobi equation. So what happens is you take this iconal form of the wave function, you plug it into the Schrodinger equation, you get out a real and an imaginary equation from that. The real equation is this one, which is exactly like a Hamilton-Jacobi equation for this Hamiltonian, the kinetic energy, the quantum potential, and the potential energy. And then you also get out from the imaginary term the continuity equation, which comes out in this form with the r's, but you can rewrite that in terms of the densities. You get kind of a standard continuity equation over here. The fact that the imaginary part gives us the continuity equation is why I'll neglect the imaginary part of the kinetic energy operator later on. You'll see why. Okay, so this is just kind of bookkeeping for this. So in order for this to make sense as the Hamilton-Jacobi equation, we have to have our velocity be, or have our momentum really be mv. That has to be the gradient of Hamilton's principal function. We're using just Cartesian coordinates, not any other generalized coordinates here. And then that's going to correspond to this kinetic energy form. So the gradient, again, if grad S is the momentum, this is the corresponding kinetic energy. And this is going to be the total potential energy. That's why that Q plus U is appearing there. This is the definition of the quantum potential, which I'll derive in just a moment. Or actually, you can see it pops out right here. There's where we first get the form of the quantum potential. It just comes directly from our substitution into the Schrodinger equation. And we have a corresponding fluid current. And again, that corresponds to VA, the average flow velocity, and that's the one that corresponds to grad S. So this is all for the average flow velocity. The symmetric velocity hasn't actually appeared here yet. All right. So now I'm going to construct some of these operators I was talking about earlier, these densities. So we'll start by defining a momentum density. If I wanted to find the expectation value of the momentum, I would integrate this object, psi star momentum operator psi. And so we'll define that to be the momentum density because that's the thing we integrate over to get the total value. If I plug in the iconal form, this breaks up into these two terms, a real and imaginary term. The real term corresponds exactly to the density of the momentum grad S that we were talking about before. And then this imaginary term is the one that's going to correspond to the symmetric momentum. And so we're going to get both of those out by taking the real and imaginary parts, which again, I already talked about in an earlier slide. So the real part of the corresponding velocity here. So you have to divide out this R squared because this is a momentum density in the fluid. Gives you this form of the velocity we were expecting. And for the symmetric velocity, we get this form over here, which comes from the imaginary part of the momentum density. And if I just take this Vs and I do 1/2 mv squared, I get this form for the symmetric kinetic energy density. So this is what the symmetric kinetic energy density is going to look like. Good. Okay, and now if I go to the quantum kinetic energy density, that's going to be defined as the real part of this object. And again, the reason I'm ignoring the imaginary part here is because it's related to the continuity equation in the Schrodinger equation that comes out of the Schrodinger equation. So this is the thing we would integrate to find the total kinetic energy. So that's the density. And again, all we're concerned with here is the real part. And that breaks down into two terms. One is the quantum potential density. So it's the quantum potential from the last slide times R squared. And then here is the average kinetic energy density, again, times R squared. So the lowercase letters just indicate that I'm talking about a corresponding density. So it's just a factor of R squared that separates those two. And we'll use that kind of generically throughout the rest of the talk. So the quantum potential energy density can be written in this form. And this actually can be expanded out into this form. So this is just a simple vector calculus identity to break it up into these two terms like this. See, this term is the thing we just identified as the symmetric kinetic energy. And this other term over here that's left is the thing we're going to define to be the reduced quantum potential. So that's where we're getting the reduced quantum potential. So we from the momentum, we came up with what we expected the symmetric kinetic energy to look like. And here we see that it pops right out of the quantum potential as an always positive term. Okay, so here's our form for the reduced quantum potential. And now if we see that KQ is our total quantum potential energy density, I can take that, write it as Q plus KA. I can take the Q and break it up into QR and KS. And then I can put the QS, the KS, and the KA together into KC, classical kinetic energy. So I have these two different equivalent representations of the physics that's going on here.
So here you didn't need to make that symmetric assumption, it just sort of falls out of the form.
Yeah, I didn't have to make the symmetric assumption, but in order to get this right here to work, KS plus KA equals KC, I had to have the symmetry. That's how I got the cross terms to cancel.
I see.
Yeah. Okay, so this was to go to the question you were asking, Matt. So the symmetry requirement does not uniquely determine the trajectories of the fluid particles. It doesn't. It's also not determined by the fact that VS can't produce a net flow. There are different solutions that can give that answer, but I'm going to give one possible interpretation of this. And I think it's reasonably well motivated. It's a little bit weird though. So one way we can think about this is that at each point, there's a little infinitesimal vortex, and the fluid orbits around that vortex with effectively an infinite period, but at a finite velocity. and the velocity that it orbits at is the symmetric velocity. And if I have two particles in opposite sides of that orbit, as they go around, at all times their velocities cancel, and so we get the symmetry condition from that. And I could have many particles in that orbit. So we're going to imagine at each point there's a little infinitesimal vortex, and this vortex kind of lives beneath the scaling at which we coarse grained, which is why it looks the way it looks in the continuum fluid picture. But if we kind of zoomed in on the fluids, then at some microscopic scale, we would see them doing this little vortex motion. And again, this is just one possible interpretation. So this whole slide is pretty speculative. Make sure that's clear. But yeah, if we had this explanation, it would satisfy the symmetry. It would explain why the particles don't go anywhere. They don't contribute to the flow because they just stay in this little tiny circular motion. This solution is inspired by stable vortices and orbits that appear in degenerate superposition states where the energy is stored in Ka, or some of the energy is stored in Ka. And I'll show an example of that next to get an idea. And if I have these infinitesimal vortices and orbits, they behave basically like a local energy storage mode. It is still kinetic because they're going around, but it acts in most ways like a potential energy for the fluid. And so that's why this really just popped out of the term that we were thinking of as the quantum potential before. So with this kind of picture, we can go back and think about our animation and explain why we got that total surface that we got, even though some of that actually was this type of energy creating that shape that acts just like a potential energy in all ways. Okay, so here is a degenerate superposition of n equals 1 for x, n equals 2 for y, and vice versa in a 2D infinite square well. So that's the superposition, and notice that I've got an I here for the coefficient. That's what makes this unusual vortex we get here. So the first thing to notice about this state, it has a definite energy value, and because of that, its density doesn't change in time. If I just take the mod square of this, it's going to be some constant in time. This part will drop out. But there is motion in this system. The flow velocity, the gradient of s, is not 0. And I've got a momentum diagram here which shows arrows for the momentum and streamlines for the momentum. The pink colors here have to do with superoscillation. So I'll explain what's going on there later on. But the dark pink here is where the quantum potential goes negative, and that actually corresponds to regions of superoscillation. And the lighter pink is where the reduced quantum potential goes negative, which is a broader region. And that will correspond to an alternate definition we can give for superoscillation. So it depends, if you want to define superoscillation, it depends whether you think the total kinetic energy is Ka, or whether you think total kinetic energy is Kc, which includes this extra term. That's going to tell you whether you're exceeding some kind of classical bound. Okay, so the shape of the quantum potential energy, or quantum potential here, is this funnel. So we have an actual vortex here, and you can see that the motion, the Ka motion of these fluid particles is just going around in orbits around this thing. And as we get right down into the center of this funnel, the orbits become pretty much circular. And that actually tells you as an interesting corollary that the quantum potential has to be a 1 over r squared potential in order to get these circular orbits in the center of this vortex. So it's not that potential out here, but it approaches 1 over r squared as you go to the center of this vortex. So there's a unique form to the vortex. I found out that that's an observation that was made by some other people in the 90s. I was not the first to figure that out. Okay, so in this case, some of the energy is of the average flow type, because this thing really is going around in a circle. There's also symmetric energy stored here, but that, again, I've included both of them here in this. This is total Q, not reduced. So you really see why we're getting the flow we're getting and the total energy. So some of what's making up this shape is energy that's stored in symmetric kinetic energy. But this is an interesting example because it shows that we can get something that has a stable density by having a stable vortex. And so the idea for the symmetric kinetic energy being infinitesimal vortices kind of follows from this. Just take this picture and shrink it down to be infinitesimal, and you can see how you could have stable kinetic motion kind of trapped around that vortex. Any questions about this at all? So yeah, so this is a nice case because, like I said, if you go right down to the middle here, you see very straightforwardly that you get all of the classical equations you expect for uniform circular motion, and the central force is just the force coming from the quantum potential. That's what's keeping it going around in a circle. Okay, and then just to give a little bit more depth for that, this is the same example, but we can look at a number of different characteristics. So this is the actual density of the fluid in that vortex, the stable density of the fluid. And then these are the two-dimensional densities of all of the other interesting types of energy we were talking about here. So this is the total quantum potential, which goes with the average kinetic energy. So this is kind of the picture where we can see the flow more intuitively. This is the probably more physical picture where I have the total classical kinetic energy and the reduced quantum potential energy. This is what the symmetric energy term looked like. So the sum of these two here is this. And also I know that Q is breaks down. So the sum of this one and this one is that one. You can see how all these things fit together in these diagrams. I've done these all as densities so that we get well-behaved functions, because the vortex, actually goes off to negative infinity and the kinetic energy goes off to infinity. But if you multiply by r squared, they become well-behaved functions.
So reduced quantum potential is a much lower middle dip, right?
Yeah, it goes down to -80. That's because it's really, you take this one and you subtract out this part, which has this spike in the middle that goes up 40. And so that's why this one is twice as deep over here, because you took out another always positive kinetic energy term. So these two are well-behaved kinetic energies, they're always positive. This just gives a little bit more intuition for what's going on here. I don't know, maybe, I don't know how much you can get out of looking at these pictures for a few seconds, but. Okay, so now we'll talk about some of the other details. So as I mentioned earlier, if we want energy to be locally conserved, we have to pay special care. So in a classical fluid, if I had a classical energy density E equal to a kinetic energy density plus potential energy density, this would satisfy a local continuity equation of this form, the energy density. This says energy is locally conserved. And in this case, the current is just the energy density times the flow velocity of the fluid. In our case, we have this extra term Q in the energy, and we'll call K the flow kinetic energy. We can also write it like this, depending which form we want to work in. But the flow velocity is VA. That's the one that corresponds to the fluid actually moving along. And if we plug this in, we're going to find that equation 1 is not satisfied. So we don't appear to have local energy conservation, which looks like it's a problem. But we can fix it. So if we allow that the internal reduced quantum potential energy, so whether you're in, there are these two different pictures, and there is a physical difference between them, because in one case you think of the whole quantum potential as a kind of potential energy. In the other case, you pull out the symmetric kinetic energy from it, and you think of what's left, the reduced part, as being the internal energy. So at this point, we really have two different physical pictures for how the dynamics of the fluid actually work. But in most ways, they behave the same. So if we allow that energy that's inside of the particles of the fluid can flow from one fluid particle to the next, it can diffuse through that material, then we can get another kind of flow velocity. So in addition to the flow of the fluid itself, we have this this flow of the energy through the fluid. So even if the fluid was at rest, that energy could still flow in principle.
The mechanism of that is unspecified.
Say that again?
But the mechanism of that energy flow is unspecified.
That's right. We're just basically the question here is it possible to restore locality? And it turns out that we can by introducing an extra velocity that would be a flow velocity term for the quantum potential. So it still flows along with the fluid, that's the VA here, but it has this extra velocity term, which is a different kind of flow between fluid particles. And if we add that in, then if we write down our continuity equation in this form, where I've said that the kinetic energy and the external potential, just like in the classical case, those can only move with the fluid. They're just external, those energies are external properties. So if I know where the particles are, then I know what the kinetic energy and potential energy are in those cases. But I have this new velocity here for the extra sort of dissipative flow of the, though dissipative is the wrong word, it's not really dissipative, but spreading through the fluid. We have this extra velocity term here. So it turns out that we can solve for the condition that this is 0, and that's what we get is this form. So this is the quantum potential times the velocity field equals this function of the density and the Hamilton principal function S. And then there's also this free constant term, which is just any field that has 0 divergence. this is what we get if we do this where we treat the total quantum potential as internal energy. And then if we do this where we treat only the reduced quantum potential as the internal energy, we get something pretty similar. And so this is now the reduced quantum potential times the velocity, and there's a difference of a factor of 2 in the terms that appear here. F is the same, divergence free field. So we can, if we suppose that there's this extra flow velocity, then in fact we get back completely local dynamics. Even the energy is locally conserved. So going forward, I'm just going to assume that whichever picture we're working in, we've taken this velocity condition to be true so that we have local energy conservation. Any questions before I go on?
Have you plotted that vector field to see what it looks like?
No, I haven't. It's something I'm meaning to get to, but I haven't done it yet. Yeah, I have a feeling that it's pretty ugly. But yeah, that's something I want to look at. This is one of these things where I think it's ugly, but I actually think that once we go to a relativistic case, it'll probably be a little bit better behaved, though I don't know that for sure. Okay, so I'm going to assume that we've chosen V so that energy is locally conserved. And now we can look at the continuity equations for each of these 4 types of energy separately. And individually, the density or the continuity equations won't equal 0. They're going to equal some source and sink terms. And by looking at how those source and sink terms match up, we're going to see how the potential energy density is being converted into kinetic energy density, and how the quantum potential energy density is being converted into kinetic energy density, and vice versa. So we're going to see all of the ways that energy is exchanged between these 4 different types. And it turns out that even though there are many possible ways, only these terms survive as being non-zero when you go through that whole calculation. So this first one isn't even a linkage between different types of energy. That's just if the external potential is changing in time, then that's going to be changing the external potential energy density. But this term over here is the one that we would get from the standard classical fluid picture. This is the exchange between the kinetic energy density and the potential energy density. And these other terms involving the quantum potential don't have any classical analog. So once we have the quantum potential, we have these extra things going on. So this is the way that the coupling works between the reduced quantum potential and the external, or the average kinetic energy. So this is the power density being transferred from Ka into Qr. And then there's also energy being exchanged from Qr into Ks. So all the energy that flows, it can flow from the external potential into the kinetic, from there into the reduced quantum potential, and from there into the symmetric kinetic. So the quantum potential acts as an intermediary between these 2 types of kinetic energy. And you can see even kind of more reason why rolling those together into a single potential energy makes a lot of intuitive sense. So that's how that looks in the one picture. And then the other picture, we combine these 2 kinetic energies together. That's how it ends up looking. But these are all of the different types of energy exchange that happen. So these are the ways that energy is locally being converted from one type to another as the fluid evolves. And again, we've already assumed that we have local conservation, which is why we don't have to worry about what's going on with the quantum potential continuity equation. That's the one where we would have the violation of local conservation of energy popping up, but by putting in the velocity, we fix all of those terms so that now, including all of these energy transfers, the total energy continuity equation is equal to 0. So energy is locally conserved. Any questions about what's going on here?
My only question is this V field you got, why isn't that contributing to the energy densities?
You mean the symmetric velocity?
No, this extra V that's transferring energy.
Well, that's really just a flow velocity, and so all it's doing is redistributing energy within the kinetic or within the quantum potential. It's not a coupling between different kinds of energy. So that's what it did. It meant that I can take some quantum potential energy from over here and put it over here because I have a flow velocity.
But it doesn't contribute its own kinetic energy.
Well, it doesn't. Yeah, I mean, it is not a physical thing moving. It is just a flow of energy that's sort of already there, stored internally.
Okay.
So it does not correspond to the particles actually moving. It just sort of says I have 2 particles side by side, and this one loses some internal energy, and this one gains it. And that's how you get a local flow of this energy, this kind of energy. But again, it's staying quantum potential. So these are showing powers where we're switching from one type of energy to another. In this case, it's just moving the quantum potential around from one place to another, but it stays quantum potential.
Okay.
Okay. And now let's see. I have no idea what time it is. How I'm doing on time. Okay,
You're halfway through.
halfway through.
Isn't that right?
No, it's-
We are like.
Well, halfway through.
Based on the
Oh, wait, sorry.
A lot of these are pictures, so I can try to kind of rush through the rest of it just to talk about the superoscillation stuff. Okay, so if we look at the time-independent Schrodinger equation, we get this relationship. And so this is just the total energy E, the energy eigenvalue. And we can see from this that every particle in the fluid has the exact same total energy E. Every particle everywhere in the fluid has the same exact amount of energy, and that is the energy eigenvalue. If we define superoscillation to be a case where the kinetic energy exceeds what we would call the classical bound, which is just the total energy minus the potential energy, so Ka greater than EU or E minus U. From this, we can see that that's equal to Ka plus Q, and then we can subtract the Ka from both sides here, and we see that the condition really is just the quantum potential is negative. So for an eigenstate, if the quantum potential is negative, then at that region, we have superoscillation. The local kinetic energy exceeds what we would expect to be the classical bound. And if we go to the reduced quantum picture, reduced quantum potential picture, we get pretty much the same story. We now define superoscillation as the case that the classical kinetic energy exceeds this bound E minus U. So that now includes both the average flow one and the symmetric one. So it's a different quantity. But if that's the kinetic energy, then superoscillation should correspond to where that is more than the classical value we would expect. And if we do that, we get a similar expression. And now we say that the condition for superoscillation is that the reduced quantum potential is less than 0. So it falls out the same way. This works really well for energy eigenstates, and we just saw that it works for that degenerate superposition state where we had two different eigenstates, but they have the same energy. And that's when we got that vortex case we were looking at. But we'll see that it does not work for energy superposition states. Michael Berry did all of this for eigenstates, and then he missed that there was a difference and just assumed it applied to superposition states, which it actually does not. It's a little bit more complicated for eigenstates or for superposition states. So this is what we get if we take the corresponding time-dependent Schrodinger equation. So instead of E, I've got this term, the negative partial of S and T. And we can see now that that thing is the classical energy density. So the energy density of a given particle in the fluid is this value, which is no longer going to be uniform. So now different places in the fluid, the particles that are there have different total energy, not just different kinetic energy, but different total energy. So if we think of that as the local energy of the particle, we can define superoscillate, or we can define a local band limit. So instead of saying that the superoscillation bound should be E minus U, we'll say that it's this energy minus U. That's what we think is the real energy density that's there. And if we do that, then we get out what I'm defining to be soft superoscillation. So this is, we're not using the energy eigenvalue, we're now using this value, which is going to be different at different locations. So this gives us a new definition for superoscillation. And this new definition is the one that corresponds to these bounds, Q less than 0, QR less than 0. So this is what Michael Berry missed, that he just assumed that when I made this switch, these bounds would still correspond to the limit E minus U, but they don't. They correspond to this partial S partial T minus U. And so it makes sense to still think of this as a kind of superoscillation. It's certainly, consistent with these zeros being the bounds of the regions where we have superoscillation. So this is kind of a new notion of superoscillation, a new way to define it. And then the standard thing, I will now call hard superoscillation. And that's where we have some band limited superposition. E plus is the highest energy in the band. And now E plus minus U should be our classical cutoff for superoscillation. And then we see we get a different condition. It's just the difference between the partial S partial T and the highest energy eigenvalue. So that becomes the cutoff in Q and QR for those regions of hard superoscillation. Okay, what does superoscillation do? So in an energy eigenstate, there's always hard and soft superoscillations in the classically forbidden regions. And for energy eigenstates, they're the same thing, because partial S partial T is E, the same value. So we see that in a classically forbidden region, we've got E minus U being less than 0. That's equal to Q because K is 0. And so we see that everywhere we're in a classically forbidden region, we're automatically at a place where we have superoscillation because the quantum potential is negative. And if we go to superposition states now, the classically forbidden region is where we have this condition happening for hard superoscillation. And so we will now see that Q less than this value here is always going to be the region of hard superoscillation. And then because Ka is always positive, this number is always less than this one. And this was the bound for superoscillation. So whenever we're in a region of a forbidden region, we always have hard superoscillation by definition. This is always going to force the quantum potential to be negative, or sorry, below the bound for hard superoscillation. And then if we go to the other picture, QR and KC, we find that we again always get a region of hard superoscillation where we're in a classically forbidden region. So this is completely general. Whenever we're in any region that's classically forbidden by either standard, in either picture, we're always getting superoscillation. It's always the hard kind, but the soft kind always, whenever you have the hard superoscillation, the soft kind is also always there. It's just a stronger condition. We can finally define a new notion of classically forbidden regions. We can get locally classically forbidden regions using our local energy density, the negative partial S partial T. And if we do that, we find that Q is less than negative Ka, or in the other picture, QR is less than negative Kc. And again, both of these are below zero. And so these are regions of soft superoscillation, whereas here they were below the bound that was related to both energy, the maximum energy and the partial S partial T. So in both cases, even giving this other definition for what is a classically forbidden region, we always find that the regions have superoscillation. They also appear near nodes in R, and they appear in interference phenomena. And in general, the dips that we saw driving the motion, those were below zero. And so the superoscillation in the dip is actually driving the motion in our superposition state that we saw in the animation earlier too. Okay, so now pretty much everything that's left are pictures. So this is the ground state of the harmonic oscillator. This is showing a number of the different energy densities. This U is hidden behind Kc and Ks in this case. They're the same for this particular one. So you see that the average kinetic energy is zero. You can see where the reduced quantum potential is. The dark pink is the classically forbidden region using the standard Q picture. The light pink includes now the QR picture. And so we can see this is where the reduced quantum potential becomes negative. This is where the quantum potential becomes negative. And I've drawn the zero for the densities at the corresponding eigenvalue on this sort of backdrop harmonic oscillator potential. So you can see exactly where we enter the classically forbidden regions. And you can see that's exactly where the quantum potential, the two different kinds become negative.
This is total energy zero or something?
This is just total energy h bar omega over 2. This is the ground state of the harmonic oscillator.
But we have it at zero on the left.
Yeah, I've plotted all these energy densities at zero, and I put the zero at this is kind of a mixed diagram. So like really the harmonic oscillator potential has no units on here, but I've put the zero of where I've drawn all the energy densities at the energy eigenvalue relative to this.
Gotcha.
So that everything crosses exactly at the forbidden region, so you can see it all visually.
Okay, but this is the ground state.
Yeah, this is the ground state. And then this is the first excited state, same potential, just drawn with a different scale. And you can again see where the forbidden regions begin. And now you can see that we have a region that's got soft superoscillation, or sorry, eigenstates hard and soft are the same. This is just a region where we have superoscillation in the QR picture, but not in the standard Q picture. So we treat this as a quantum potential. We have the superoscillations that appear in the middle for higher energy eigenstates, but the superoscillation for the standard Q picture only appears at the outside edges in the classical forbidden regions. Okay, this is our quartic double well potential again, so you can see the blue. So this is the same one I used for the animations. And this is showing the energy densities for the ground state, and you can see all the same stuff happening with where the forbidden regions are. I'm not going to spend too much time on this. And that's the first excited state. So it was the superposition of those two states that we saw making the animation in that I showed earlier on. Okay, and now we've got streamline diagram. So this is for infinite square well, the same superposition for first excited state and ground state. How does this evolve in time? So it just oscillates back and forth. So you can see the fluid streamlines. Fluid all starts on one side, or mostly starts on here. moves across, moves back. Now the regions, we're in the QK picture, and this is a superposition state. So there's a difference now between hard and soft superoscillation. The light gray is the soft superoscillation, the dark gray is the hard superoscillation. And you can see basically these are the dips that are driving the motion. The potential gets canceled out. We have these dips that move across, and as they move, they pull the fluid across them. So the fluid's actually dips moving one way, fluid's getting pulled across the other way. And that's driving the motion. And then if I switch to the other picture, QRKC, again, I have regions of hard and soft superoscillation, and this is what they look like now. And so I have a bunch of symmetric energy stored at the edges, which was not there in the previous picture, where they, up against the walls. Okay, the reason to show these is that if I now switch to harmonic oscillator, I get something that looks pretty similar. It's not exactly the same, but the dynamics looks pretty much like it's doing roughly the same thing. I still have this dip moving back and forth, pulling the fluid across. This is in the QKA picture. There's the same thing in the QRKC picture. Okay, and now let's switch to a finite, there's an infinite square well, but now there's a finite barrier in the middle, and I have tunneling through that barrier. And this is what it looks like. So I always have superoscillation everywhere in the classically forbidden regions, hard superoscillations. That's why the whole barrier is dark gray. And then I have you look, there are little fringes of light gray on the edges here. And those are my regions where I have soft superoscillation. So the light gray is bounding the region where the quantum potential Q is negative. And here it's bounding the region where the reduced quantum potential is negative. And so this is the same thing, but now look in the QRKC picture, so you can see where the energy is. And finally, back to our quadratic double well potential. So this is just streamlines for the animation we watched at the beginning. But now you can see where the regions of superoscillation are on this diagram. So again, the dark gray is the hard superoscillation, the light gray is the soft superoscillation. So they're almost the same, but they're not actually exactly the same. Okay, and then here it is in the QRKC picture. So the point of all of those four examples, they were all superpositions of the ground and first excited state, that all different potentials, but when you actually get down to what's going on with how the fluid dynamics work, because of the quantum potential, they all are almost the same. The difference between the cases with the barrier in the middle and not was that we had to have a stronger superoscillation in the middle to get through the barrier. But you actually look at how the fluid streamlines moved, in all four cases, it was pretty much the same. Okay, here's just to see quickly the other interesting thing that happens with these. That when I have, this is a band limited Gaussian pulse, so I take a Gaussian, I cut off the band at some point, and then that allows me to define hard superoscillation above the band limit. This is a Gaussian pulse coming in and reflecting off of a wall, and this is halfway through the reflection where the nodes form. So you can see that there are these stripes of soft superoscillation that are there, and then we get regions of hard superoscillation that form around the nodes as the nodes form, and then vanish briefly at the node and then reappear again after it. So these here correspond to that places where the quantum potential had that negative singularity in the animation. So that whenever you have a node in the density, you get a singularity in the quantum potential. So you can see the superoscillation is playing an interesting role in how the interference fringes appear in a reflection case like this. It's part of what's guiding the motion, and it's creating dips at the locations of the nodes. And then this is in the QRKC picture. And then just to see something a little bit more extensive, here is a 1D Mach-Zehnder interferometer, same story. So I've got a band limited Gaussian pulse that comes in, splits at this beam splitter, reflects off these walls, recombines up here, this beam splitter again, and goes back together. And so you can see that I've got, to get this beam splitter, I just did a finite potential barrier, and I tuned it so this would be 50-50. So you see I've got hard superoscillation in the barrier. That's a classically forbidden region. And I get these stripes of hard superoscillation where the dark fringes form. And again, the zeros appear right on the center of it, right here where the reflection is halfway done, and here and here. So this is what the superoscillations look like in the QKA picture, and then in the QRKC picture, it looks pretty similar. The regions are always a little bit larger because QR is always less than Q, because I subtracted a positive quantity to get from one to the other. Okay, that is everything that I wanted to show for examples. Summary is just to recap what I said in the introduction. So this gives us a way to put all the physics back into space-time. once we use this way of interpreting the single particle equations that we get out, we basically just start talking about classical fluid dynamics. Everything weird that's happening is because we have this new kind of potential energy that appears. But once you include that as part of your Hamiltonian, your classical Hamiltonian, you describe all of the Schrodinger fluid dynamics just as classical equations of motion. And you have to now think of this quantum potential, or maybe the reduced one, as a kind of internal energy to get all of this to really make sense. The first picture explains the bulk flow. When we're actually looking at animations of things, the QK picture makes the most sense. You can think of Q, total Q, as a kind of potential energy that the particle is moving around in. And then if you switch to the QRKC picture, you get something which is probably a little bit more physical. It explains why we have motion in stationary states, but it's less intuitive for looking at the flow of the overall bulk fluid. Non-classical behaviors are due to the quantum potential. So then the final discussion points here are that this gives a really nice intuitive way to visualize what's going on in the evolution of quantum states. We can do it all with classical reasoning. So I think that's a big advantage to thinking about things in this way. I expect most of these cases are going to generalize to relativistic scenarios. It's important to emphasize that in the non-relativistic case we're working with, the velocities near singularities or near nodes in the density go to infinity. And so if we're trying to say this is going to be a local theory, that's a problem. We have infinite velocities. But there's good reason to think that when we go to a relativistic case, even though the momenta go to infinity, the velocities won't at those locations. And so we think that all the speeds will be bounded by c in the relativistic case, and that will resolve the problems around singularities. And there's some people who've done some preliminary work on relativistic generalization that seem to support that that's going to work out, but it's not a done deal yet. The final point to make here is that what I did here works just fine for a fermionic case where I'm talking about an electron. I have a well-defined particle number, but if I'm talking about bosonic fields, things are a little bit more complicated. But I think that this whole model can be generalized to handle bosonic fields. And then you can have a definite conserved fluid, but when you measure the particle number, you'll branch into different local worlds where you might see different particle numbers in different worlds, but there will still have been an underlying conserved flow of fluid. And this is how this should connect up to a lot of what's been done in optics, where we see some pretty similar things, and sort of like an optical quantum potential. So I think that all of this will generalize over to that case. All right, that's everything. I forgot to turn on my thank you slide at the end. So this is my last slide. Sorry if I ran a little over. Hopefully that would just cut into my delay time in the middle.
Good. We have time for a few quick questions. Is all good?
Yeah, thanks, Kai, for the nice talk. Could you please remind the definitions of Q and QR?
Yeah, so way back. Okay, so Q is popping directly out of the Schrodinger equation here. So when I take the Schrodinger equation and I write it in the equinal form, I get a real and imaginary equation. The real equation has this term right here.
Right.
And that's the thing we call the quantum potential. So that's where it's coming from. Because if you interpret that as an energy, then this is just a Hamilton-Jacobi equation for this Hamiltonian. And so that's where the idea of treating it as a kind of energy comes from, a kind of potential energy. And then to get the reduced quantum potential, I do that here. So I take the quantum potential and I can just expand this term into these two terms. This is just a simple vector calculus identity. And now I see this term here is always positive, and it corresponds exactly to what I was expecting my symmetric kinetic energy to be.
Right.
Except that was the density here. So a difference by a factor of r squared. And so this is how I see that I automatically have this always positive term that really falls right out from the quantum potential directly. And so instead of the original quantum potential, I'm left with this term here, which is going to be the reduced quantum potential. And this one has that nice property that when I integrate it over the whole fluid, it's zero, whereas the original quantum potential doesn't, because it includes both the symmetric kinetic part and the reduced part.
Yes, so I have a follow-up, which is, so I see that both Q and Q are defined in terms of a Laplacian.
Yeah.
So in our, and you see the conditions for superoscillations to be Q for energy eigenstates, Q less than 0, Q are less than 0. So in our Bessel function work, we proposed this new definition of superoscillation or supergrowth in using the Helmholtz equation, which turns out to be in terms of Laplacian as well, instead of the usual way of taking logarithmic derivatives.
So you found some condition on like Laplacian being negative or something like this?
Yeah, so there are some problems with the existing definition in terms of the first derivatives. So we basically proposed a new definition using the Laplacian. And I wonder if there's some sort of connection.
I mean, it seems like maybe I've arrived at almost the same definition you're talking about, because I came at it from a somewhat different direction.
Right.
Yeah, I mean, the way that I define superoscillation kind of just followed from what Barry had done. I just defined the classical bound to be the energy minus the potential energy.
Right.
Minus potential energy. And it follows from that directly that the quantum potential being zero is the cutoff.
Speaking of cutoffs, we have to vacate because there's another event happening. So we will continue the discussion and questions informally. Thank you, Kai, again.